In this video, we're going to finish the last sections of Chapter 15, looking at sections 15.5 and 15.6, Introduction to pH and Neutralization. So in order for us to understand pH, we need to know that molecules of water, in this example, are going to react and exchange hydrogens. And so we'll see a H3O+, also known as a hydronium ion, and an OH-, or the ion we know as a hydroxide ion. And so we can see that based on our double arrows, we know that these are going to be in equilibrium, and our concentration of H3O+ and our concentration of our OH- are going to be about the same. Now, I don't need to hold you accountable for these numbers, but what I do want you to know is that for acidic solutions, our hydronium ion, our H3O+, is going to be in greater concentration, and in basic solutions, our OH- molecule is going to be in higher concentrations. And this makes sense if we know what acids and bases do. So pH, again, is going to be a log ratio of our hydronium ions. And while we're not going to deal with any math for this part, what you need to know is that our pH scale goes from 0 to 14. Our lower pHs are going to be acidic. And so as we go down closer to 0, we're going to have a higher acidity. So 1 and 2 would be a stronger acid than a pH at 5 or 6. And the reverse holds true for bases. So a highly basic compound would have a pH of 12, 13, or 14, while a slightly basic compound would be 8, 9, or 10. So as we go up to 14, we increase in basicity, and as we go down to 0, we increase in acidity. So our neutralization reactions are going to involve us looking at species when we combine both acids and bases. And so two of the most important acids and bases that we've used for examples are hydrochloric acid and sodium hydroxide. When we combine those together, we're going to get sodium chloride and water. And often chemists sometimes actually exclude our salt and our chlorine ions, or our sodium and our chlorine ions, because they're not really adding much to the reaction. They're just holding on to our H and our OH groups, and those are the ones that we care about. And so often we'll see something called a net ionic equation, where our spectator ions, or our sodium and chlorine, are going to be removed out. This is again something you'll focus on more if you end up taking another chemistry course. For our purposes, what we need to know about pH is that when experiments are done called a titration, we actually are using the concentration of an acid or base to help us figure out the other concentration of an acid or base. And indicators are often used to tell us when pH has changed. And we talked about this, or you saw this phenomenon when we reviewed phenolphthalein in lab way back in probably week 3 or week 2 of the semester. So these are the kind of questions you should be comfortable answering. If 22.59 milliliters of a 0.1096 molar HCl solution is used to titrate 25 mils of NaOH, what is the molarity of the base? So we can write out our chemical reaction. We know that combining these two species is going to give us sodium chloride and water. And what we need to do now is to figure out how many moles of HCl we have to neutralize our sodium hydroxide. So we need to calculate the same amount of moles, and then in order for us to get molarity, take those moles and divide them by our volume. So let's walk through this one. Our knowns, again from the question, are 22.59 mils of 0.1096 molar HCl, and we know we have 25 milliliters of NaOH. So we're going to convert our 22.59 mils in order for us to figure out how many moles of acid we have. So we'll multiply by its molarity, dividing by 1,000, because we know molarity needs to be moles over liters. We'll multiply by our 1-to-1 ratio, and that tells us we need to have 0.002476 moles of NaOH. Again, we look back at the question, giving us our volume of the base. We then take our moles over liters. Again, notice we put our 25 milliliters into liters, converted that, giving us 0.09903 molar NaOH. Now, here's another example with the same type of question, but what I want to point out here is we're looking at the molarity of an NaOH solution if we have oxalic acid. And so we can see the formula of oxalic acid being H2C2O4, and so that means we're going to need a coefficient of 2 on our NaOH. This is going to be important for our mole-to-mole ratio that we'll set up in a second. So we'll do the same thing here. We're going to start with our 0.243 grams of H2C2O4, our oxalic acid, multiply by its molar mass, multiply by our molar ratio here, giving us 0.005398 moles. Again, we have our volume in the question, so we're going to divide by our liters here. So we'll divide our moles that we just calculated for, divided by our milliliters converted into liters, giving us 0.246 molar NaOH. You can see in this one I didn't give you the concentration, so it was very easy that if we knew how many grams we had, we can just convert that to moles, multiply it by its molar ratio. That gave us the amount of moles we would need in order to titrate or cancel out our NaOH. So in order for this, you always need to make sure you're looking at the reaction or you're writing your balanced chemical equation to get your correct molar ratio step. Try this example on your own. Pause the video now. What is the concentration of a nitric acid solution if 10 mils of the solution is neutralized by 3.6 mils of a 0.2 molar NaOH? Answer is A. Let's see how we get there. We wrote our equation out right here with our formulas for nitric acid. Make sure you knew it was HNO3. That might have hurt you if you tried to balance it with the wrong formula. Our knowns, again, we're going to start with 3.6 mils of NaOH right from the question, multiply by its molarity, 0.2 over 1,000 mils, by its molar ratio, and we know we need to have 0.0072 moles of HNO3. We'll then divide that by our 10 milliliters, or 0.01000 liters, giving us 0.072 molar nitric acid. That's it for Chapter 15.